Okay, let's start right away with basics of orbital mechanics, and we're going to answer a couple questions today. How does spacecraft get into orbit? How do they change orbit? And how do we get to the moon? Or more specifically, what is the delta V required to get to an elliptical orbit that reaches the moon? So let's say you're on the Earth and you're on a really tall mountain and you shoot a projectile out, like a cannon or a gun. If you shoot straight out fast enough, it's just going to go into space. And if it's slow, as you can expect, the trajectory will just make the bullet fall to the earth. In between, there's a speed where it will get into orbit and it will be in constant free fall, where it's constantly falling to the ground, but it can't catch up to the ground. So this projectile, the free body diagram shows us that the only force acting on it is the force of gravity radially into the center of the earth. And since it's going on a circular path, we can sum up the forces using Newton's second law of motion to say that the gravitational force is equal to the centripetal force. Gravitational force is big G, big M, small m over r squared, and the centripetal force is mv squared over r, where big M represents the mass of the Earth and small m represents the mass of the orbiting satellite or projectile. Canceling some variables out here, we see that the velocity is equal to the square root of gm over r. Gm can be represented by mu as a constant, and this is the equation for velocity of an object in circular orbit, and this is a constant velocity in the entire circular orbit. So mu is the standard gravitational parameter, and this can replace gm to make the equation a little cleaner. So now that we have the formula for the exact velocity our orbiting spacecraft needs in order to maintain its circular orbit, what if we want to increase our orbit to, let's say, from 1 here to number 3? This is what's called a Hohmann transfer. The exact definition is an orbital maneuver used to transfer a spacecraft between two orbits of different altitudes around the central body. This was named after German scientist Walter Hohmann. So currently we're in orbit number 1 here with this rocket, and in order to reach a higher altitude, we're going to have to do a burn, just like pressing the gas in your car. In your rocket, you're going to increase the throttle for your engines to burn for a certain period of time and increase its speed and achieve its elliptical orbit. The interesting thing about orbiting spacecraft is that when you do a burn, you'll stay in this elliptical orbit number 2 until you do a second burn that corrects your trajectory to a circular orbit again, like shown in this diagram for number 3. Once we're in an elliptical orbit, there's a separate equation for instantaneous velocity because the velocity is no longer constant like it was in the circular orbit, and is dependent on the position. So just some terminology here. This is using the same basic geometry of an ellipse with the semi-major and minor axes, but we're mainly only interested in the semi-major axis. The perigee is the shortest distance between the center of the body to the ellipse, and the apogee is the furthest distance. The orbiting body or spacecraft is fastest at perigee and slowest at apogee. So Kepler's second law of planetary motion says that the sweep area for an orbiting body is equal for an equal amount of time. So what that means is, let's say you're getting faster and faster at perigee and you traveled from point A to point B for a certain amount of time, delta t. That area you sweep relative to the center of the orbiting body is the exact same as if you're going towards apogee, where you're much slower and you're going from point C to point D. This is of course not to scale, but the idea is that these swept areas are the same, given that the delta t, or the time that it takes for you to orbit that specific segment, is the same. So the equation for the instantaneous velocity in an elliptical orbit is the vis-viva equation, which I won't derive, but is based on conservation of total mechanical energy. So the instantaneous velocity is the square root of mu times the quantity 2 over r minus 1 over a, where mu is the same standard gravitational parameter we saw before. R is the distance at which the speed is calculated, the speed that you're interested in, and a is the length of the semi-major axis of the ellipse. Finally, we have the two equations for velocity in circular orbit. and elliptical orbit. And we can now answer the question, what is the delta V required to get from low Earth orbit to the moon? Or basically, how much faster do I need to go once I'm in circular orbit around the Earth to reach the moon? So we'll first start with the low Earth orbit starting altitude, which is around 300 kilometers above Earth, and the Earth's radius, which is around 6,378 kilometers. Adding that together, you get the distance to the center of the Earth as around 6,678 kilometers. This is the distance from the spacecraft to the center of the Earth. So now we can plug in all our knowns into the first formula, and substituting in the distance we just solved for, we get a velocity of around 7.73 kilometers per second, which is our low Earth orbit speed. The rocket at orbit number 1 with this constant speed now has to speed up to reach orbit number 2. So that's the delta V we're going to solve for now in an elliptical orbit. So just to get a better understanding of what's happening from start to finish, we're circling around the Earth in this circular orbit, but we want to speed up at this point just enough so that we reach an elliptical orbit that is the correct distance to the moon. So if we speed up too little, we're going to reach these elliptical orbits, but let's say the moon is right here. We want to calculate the delta V so that we are in the elliptical orbit with the moon in its path. So all that's left to do is to solve for the unknowns in equation 2. So we'll start with the semi-major axis, which is the average between the apogee and perigee of the ellipse, which is 384,000 kilometers plus 6678. And that gives us an A value of around 195,339 kilometers. Now our R, a distance at which our speed is calculated, we're interested in the position of perigee in the ellipse, and we have all our values we need for the equation. So plugging all these knowns in, we have 2 over 6678 minus 1 over 195,339. That gives us a V prime of 10.83 kilometers per second. This is our instantaneous velocity at the perigee of the ellipse with the moon in its path at apogee. Finally, to get our delta V, we just subtract the two velocities we solved for, and we get a delta V of around 3.1 kilometers per second. So in conclusion, we only need a delta V of around 3.1 kilometers per second for our translunar injection, which will get our spacecraft from our low Earth orbit to the moon. So that's pretty much it. We answered all the questions. So the rocket will first launch from Earth, and it will push the spacecraft pretty much at a velocity of 7.73 kilometers per second. And then it will increase its speed by 3.1, and that's how we get to the moon.